so today we're going to talk more about well-definedness. Of functions and more equivalence relations. Okay, so equivalence relations. So last time we talked about equivalence relations and quotients. Okay, so last time, so recall. So given an equivalence relation, E on a set X, we defined the following things. X mod E, so this is the quotient. So this is the set of x's for x and x. And then we defined here, this thing here. So this is the equivalence class of x, and so this is the set of y and x, such that x is related to y. Okay, and so in this thing here, so note that if y is an element of this thing, then you have that these two things are the same. Okay, so those two things are the same, and we had the quotient map. So, and then we also had this quotient map here from x to x mod e. So this is a quotient map. And then I gave a warning that the warning that we had was that notation varies. So notation for equivalence classes, equivalence relations, or notation for quotients, let's say, and relations varies. Okay, so okay, and then we had an example. One of the main examples was so we defined so we had a relation on the integers, which we said that x was congruent to y mod m if and only if x minus y was an element of mz. So here so this is so in all of this, m is a fixed thing. So here we fix this and we define this relation, and this relation depends on m. M's an integer, x's and y's are integers here. Okay, so and then here the quotient. So this is z mod this equivalence relation. So this is the equivalence relation here. So this is this equivalence relation. So this was z mod mz here. Okay, and z mod mz, it had representatives 0, 1, and then m minus 1. Okay, so this was the modular arithmetic example. All right, so so what does this thing do? So this is the idea here. So z mod mz is the generalization of even and odd. Okay, so when m is equal to 2, So let's say x is congruent to 0 mod 2. So if and only if x is even, and x is congruent to 1 mod 2 if and only if x is odd. Okay, so we had these things, and then we had that this thing here. So we had this thing here, mod 2. So these are the even integers. So this is equal to 2z. And then 1 mod 2, this is the odd integers. So this is 1 plus 2z, which is really the set of 1 plus 2 times n for n integer. Okay, so like we had these this modular arithmetic, which generalized even and odds. Okay, so for 3, like for m is 3, we're going to have 3 classes. Let me just let you guys catch up for a second. I just wanted to get that out of the way. Okay.
I'm glad you at least realize it.
Yeah. Yeah. 2 hands. Huh?
That's not an n, right?
This is an m? This m here? Where?
No, go up one. The z divided by, that's just a squiggle.
This is squiggle, and this is the squiggle. So this is the equivalence relation. So this is the same thing as x, e, y. Right, so these are 2 other notations for the equivalence relation. Or you can do, sometimes you do e of x, y, you know. Whatever you're feeling. But you have to give it a name, and you have to stick with the name, right? You can use your own names for things, but you can't change names. All right. All right. It's on video too. Okay. So, okay. So for m is equal to 3, so we really divide, we are breaking the integers into 3 classes. So we have this 0 class. So this is the set of x such that 3 divides x. So let me say x and z. 3 divides x. We have this thing. This is the set of x such that 3 divides x minus 1. And then we have the other thing, the other class, which is the set of x where 3 divides x minus 2. Okay, so it's like, so another way to see this is that you can take x, an integer, you can divide it by 3 and look at its remainder. We proved before that its remainder is going to be 0, 1, or 2. Okay? And that's how these go. And it works for negative integers, and it works for, so you can let m be negative, and you can also let m be 0 if you want. Okay? So when you do m is equal to 0, the relation is just saying equality, and we talked about that before. All right. Any questions on the modular arithmetic? Okay. Yeah?
So if you wanted to get things specifically in like scripts of 3, it would be one of 3 cases.
Exactly. So like, yeah, for example, if you wanted, so sometimes in proofs, right, it's common that you'll break things into things that are equivalent mod 0. So numbers that are equivalent to, congruent to 0 mod 3, congruent to 1 mod 3, and congruent to 2 mod 3. Every integer is congruent to one of those things, okay, because the equivalence classes break up into 3 separate classes, right? And the same thing goes for any integer m. So you have m classes for each mod m, yeah.
Is that 3 divides, for 1 mod 3, is that 3 divides x minus 1 in parentheses?
Yeah, it wouldn't, so here's another thing to think about. It wouldn't make sense to have 3 divided by x minus 2. Because this would be like true or false minus an integer doesn't make sense, right? Yeah. Yeah. Okay. But maybe, you know, you guys don't know. Like maybe you missed something and I made something where it did make, you know, it's not true. Okay. Yeah. It could be confusing. Okay. All right. So, I want to talk about well-definedness. So I have kind of 2 things that I wanted to say. So in the previous class, the other class asked me, what are equivalence relations good for? Okay? I mean, they give some interesting constructions. They're useful in a lot of proofs. They're ubiquitous in math. There's another statement that I can say is that a good answer is that, well, they come up in a lot of constructions. And in particular, the official definition of the rational numbers and the official definition of the real numbers both involve equivalence relations. Okay, so I haven't said that, but they do. Maybe I'll state those at the end. Okay, I'll state the one for the rational numbers in the course of this class, right? But this is just, I just wanted to state that reason, that it's that's one good reason why we want to study equivalence relations in equivalence classes. Yeah?
So like any real number fits into a part of the equivalence
Yeah,
relation?
so I'll state it at the end, but real numbers are officially equivalence classes of sequences, right? Cauchy convergent sequences. So that's how we can define real numbers. So you can take sequences of rational numbers which converge, and then you define 2 sequences to be equivalent if they get close. Okay, and that's one way to officially define the real numbers. Okay, but let's not bother with that for now. For now I'm gonna talk about well-definedness of functions, which is something that's practically useful when we're dealing with equivalence relations. And then maybe I'll say this thing about the real numbers at the end. Okay, sounds good. Okay, so let me talk about well-definedness of functions. Okay, so we often want to consider functions with domains which are quotients. Okay, and to make these, and so in these definitions depend on representatives. Often depend on representatives. Okay, so what we need to do, we need to check, okay? Okay, so need to check that functions with equivalent inputs have equivalent outputs. Okay, so let me just write down, okay, so that's long-winded. But the motto is that you want equivalent inputs to have equivalent outputs. Okay, so we're going to be checking that equivalent inputs have equivalent outputs. And so let me give you an example. So we will show that the function, so this is a function that appears in your homework. Defined by f of x mod 4 is equal to the equivalence class of 2x mod 8. Okay? defined by this is well defined. Okay, by this we mean that equivalent inputs will have equivalent outputs. Okay, so let me just make a little note here. We could have, so this thing here, this could be two things. It could be like 1 mod 4, or, which is equal to, let's say, so 4, which is equal to 5 mod 4. Okay, so these two things are the same, 1 and 5. Or we could have something even worse. We could say 21 mod 4. Okay, so we need to check. So on one hand, f of 1 mod 4. So this is 2 mod 8. And f of 21 mod 4. So this is, this is 42 mod 8, right? And so here you can see that your inputs, so we have one class, and we want the function to be defined on the class, right? But we don't know that these things are really the same. We have to check that this thing is well defined, right? So are these the same? Okay. So this is what this is the idea, right? So we have we could have two different representatives here. So these are two representatives for the same class, right? But we need to check that the equivalent inputs have equivalent outputs. Does that make sense? Okay. So we need to check that these two guys are actually congruent mod 8. Okay. So here's the proof. So proof of well-definedness. Of f. Okay, so what do we do? So yeah.
Is there a reason that we're like assuming that x mod 4 like could be 1, like it automatically has a remainder of 1, like where you said like no?
No, I mean this is just like an example,
Just an example.
right? This is an example of two inputs. So two things. So like here, notice that the definition involves x.
So as long as x is the same as both.
Yeah. So well, x has to be equivalent, right? So it could be, I could make up some random thing where we had an equivalence relation, right? And I could write down anything as a function of x, right? And it could not be well defined. For example, if I just wrote 2x, but I didn't write 2x mod 8, this is not a well-defined function, right? Because, because 2 and 42 are not the same, right? So that wouldn't be a well-defined thing. Yeah?
Is it because you have 2x, you also scaled the mod by 2, or is that completely?
Yeah, that's kind of what's going on here. It's 2x because I scaled the mod by 2. That's the general statement. So there's a more general statement around here, but I'm just working with this example.
So you use like the sense of if like 1 mod 4 is 3, right?
So there's 4 equivalence classes of 1 mod 4. There's 0, the class of 0, the class of 1, the class of 2, and the class of 3, right? And so here I just showed that these are the same by adding multiples of 4, adding or subtracting multiples of 4. Okay.
Is there like another way of saying that like if you have something, these equivalent like classes, and you scale the number itself, its mods also scale? Like, is that like sort of like the general rule?
No. There are general rules to that effect. And so if you're interested in those general rules, you should take the proof that I do and then try and do it in general. Yeah. So that's a good observation. Yeah, there are things like that, and you are on the right track. Yeah. Okay. So let's do the proof of well-definedness of f. Okay. So suppose. So what we always do is we take equivalent inputs. X is congruent to y mod 4. Okay. So this is the same. This is the same as that. This is the same thing as this, and it's also the same as saying that x minus y is an element of 4z. Right? Okay. So this means that there exists some n, an element of z, such that x minus y is equal to 4n. Okay? Use this one. All right. And so now what we want to show is we want to show that 2x and 2y are equivalent mod 8. So we want to show two x is congruent to 2y mod 8. Okay, so that's what we're trying to show. Okay, so let's take this. So 2x minus 2y. So this is 2x minus y. So this is equal to 2, 4 times n. And this is equal to 8 times n, which is an element of 8z. So this proves this proves that 2x mod 8 is equal to 2y mod 8. So the function is well defined. Okay, so we took two inputs and we that were equivalent, and we showed that their outputs were also equivalent. That's the idea. All right. Yeah. Okay. So let's do. So let me show you something that's not well defined. Okay, a stupid, not well defined example. Okay, so we could take f of x mod 4, and then we could just do 2x, right? So this is not well defined, so it's not a, I'm going to put function in quotes because it's not really a function, okay? It's not a well-defined thing. So note, to show something is not well defined, we could have here, we could have, like, say, 1, f of 1. So this is supposed to be in let's say, f of 5 here. So this is just 5, or let's say this is 10, and this is 2. So these are not the same. So it's not a function, right? So does that make sense? It's not a function anymore. Okay, so this is not a function, but this one is, because they have equivalent outputs. Yeah?
Could you have the same example, but instead of multiplying by 2x, in the well-defined function, have like 2x plus a constant? Would that make it not well-defined anymore?
So if the constant's the same, that would make it well-defined. Yeah. Yeah. Well, yeah, it is. Because really what you're doing is you're taking a function here, from here to here, that's well-defined. And then you're taking a function from here to the next one that's well-defined, which is shifting by a constant. And then last time I mentioned that if you add two elements, that addition was well-defined in modular arithmetic. So that the sum of the residues is the residue of the sums, right? Yeah.
There's something maybe like squaring or something that you could do to 2x that would not make it well-defined, but still including the mod. Something like
Let's see.
basic or no?
Well, if you have a 2 in front, it'll mess things up. So I need to think about that. So but that's a good question. That's a yeah.
I'm trying to think of it as far as like some like transformations in linear, where like sometimes something as simple as like squaring it or adding a constant completely like just makes it now.
Yeah, I mean, there's definitely examples other from this one that where this happens. Yeah, for sure. That's definitely a thing. Yeah,
Okay.
it's definitely a thing. Yeah. Those are really good examples to think about. Yeah. Okay. but I don't know off the top of my head. All right, let me do another example of a not well-defined function. Okay, and this is going to come to this point that I said about the rational numbers. Okay, so the rational numbers are secretly a quotient. Okay, so I'm going to explain how the rational numbers are a quotient. Okay, so here's another bad example. Okay, so consider this function f of let me say it like this. I'm going to put it in quotes. Function, it's not a function. F from q to, let's say, the integers defined by, here, f of a over b is equal to a plus b. Okay? So this thing is not well defined. Not well defined. All right, so here, let's note that f of 1/2, this is 1 plus 2, and f of 2 over 4, which is supposed to be the same fraction, right? So these are equivalent fractions, right? So this is 2 plus 4. This is 3, and this is 6. Okay? So these things are not the same. So this is not well defined. Okay? So how does this fit into our equivalence class thing? Okay? So let me give you the official definition of the rational numbers. So Q is defined to be the set of A, B, an element of z squared, where b is not equal to 0, modulo an equivalence relation, where we say that AB is equivalent to CD, if and only if AD minus BC is equal to 0. Okay, so the idea here, so this is the official definition of the rational numbers. Okay? So we actually write, so in practice, this is what we use all the time, right? You guys have already used this equivalence relation, and you guys have used it for your entire life, but you don't know it, right? But this is what they are. They're pairs, but we write our classes here, A, B, as, let me put a little parentheses here, as A over B. Okay? That's how we write them when we just write them as equal to each other. You know, we say that two fractions are equal to each other, like this one and this one. And so note that A, B minus C over D here. So this is equal to AD minus BC over BD. And so these two things are equal only if, so A over B is equal to C. Can you guys see that? Okay, so we have this thing. So this thing, this is if and only if AD minus BC is equal to 0. Okay, and so you can check that this is actually an equivalence relation, and that these are, the rational numbers are just equivalence classes here. Okay, and so what we did is we tried to make, so what this does is this takes a certain representative for the equivalence class of a rational number, right? And it tries to do something with that representative, Right? And then, because it depends on the choice of representatives, this function is not well defined. Does that make sense? So this is another example of a quotient construction. The rational numbers are a quotient construction. And so this is an equivalence relation. And then you can, you define addition and multiplication as you'd expect, right? And you can show that those are well-defined operations on this, for these equivalence classes. Okay? Yeah?
So we talked about classes of like, equivalence classes of like numbers with different moduli being equal, and then those equivalent fractions. Could you have something where like, I don't know, you could have the equivalence class be like a derivative equal to like one number, or something where like you could have like f of like ax plus b, and like add maps to like a. You just take the derivative of it, and like for like any. I guess like my question is like, what other is there a set amount of like equivalence classes? Because
No, I mean, though that is an equivalence relation. So you can have two functions. If you have two functions and they differ by a constant, right? Then they can be that would be an equivalence relation. So like that's one example. So like then you could, that's the same thing as you subtract them and then you take the derivative and it's equal to 0, right? That would be an example of equivalence relation. So there's tons and tons and tons of them. There's lots and lots of them. Yeah. Yeah, here. So the denominators are not equal to 0. Yeah, d is also not equal to 0. Yeah, d is not equal to 0. Yeah. Definitely we don't let these be equal to 0. And that's why we have this not equal to 0. Yeah, for sure. Well, A, C, D is an element of this set. Yeah. So the second element is like the second element over here. Yeah. All right. So let me do another example. So these are good questions. Okay, so let me give you another example. Okay, so consider R with the equivalence relation where x is related to y, so x and y are real numbers. If and only if x minus y is an integer. Okay, so this is, okay, so then there's this thing. And so then we define this guy like this. So this is equal to r mod tilde here, like this. So this is this definition. So this is the quotient. This is the set of equivalence classes for x and r. And here, these classes again. So this class x, this is the set of y, such that x minus y is an integer. So this is, I guess, y in, I should say y in the real numbers. Z. Okay, so let's do a picture. Okay, so I'm first defining an equivalence relation, and then I'm going to define a function on there, and I'm going to check that it's well defined. Okay, so here's the picture. Okay, so here's 0, 1, 2, minus 1, minus 2, like this. And so, so this thing here, so these x's, so these guys here, this is the equivalence class of 0, right? And so here, note that the equivalence class of 0 is just the integers. So it's the things so 0, you can add an integer, or you can consider the difference of two things, and then that's supposed to be an integer. All right. So in general, right, for a general guy, the equivalence classes look like this. So observe that so they're off by integers. So for a general let's say T in R, there is a representative in the interval, let's say 0 to 1. Okay, so here, if you take so you're taking all these classes here, and if I have this 0, 1. 0 and 1 are really the same thing under this equivalence relation. But if I were to keep going here, I would wrap around, right, and find another class here. Do you guys see that? So this thing really is, the idea is that R mod, so the idea is that R mod Z is the interval 0, 1 with 0 and 1 being identified. So it's like a circle. So you go here, and then it wraps back. Okay? So that's what the equivalence class looks like. Okay? So that's this particular equivalence relation. And so now I want to define a function on this equivalence relation. Okay? So or on the quotient, not on the equivalence relation, on the quotient. A function on R mod Z, and check it is well defined. Okay, so let's do this. So here's the so consider the function f from this quotient to the real numbers given by, let's say, f of the class of some number t is equal to cosine of 2 pi t. Okay, so here is what we have. Okay, so I claim that this is well defined. It's the claim. The function f is well defined. All right. So do you guys see what I'm going to do now? So what am I going to do? Yeah.
So you're saying that the interval, like the point is the intervals of length, like 0 to 1, but you could set that to be -2 to -1, or
yeah, I could do whatever. Yeah, I could do -2 to -1, whatever. And all I'm saying is, in this claim is that, like, if I take any one of these dots, f at the dots will have the same value.
as
right?
long as you're in a space of 1, they'll all.
Yeah, as long as they're spaced out by 1, right?
You'll have the same.
You'll have the same output. So that means it's a well-defined function. I could take this representative, or I could take this representative here, right? But it's well-defined. So the picture of R mod Z is really like, it's kind of like a circle, right? Where you've wrapped up this is R mod Z is this circle here. And you've really wrapped up this whole thing, right? So you've wrapped up this whole thing, so you've wound this around into a thing, right? And so what I'm saying is that this function only depends on the class and not the representative of the class. Okay, so does that make sense of what I'm going to try to prove? Okay, I think I'm getting some nods. Okay, so what would be the first step in the proof? So
Try some values to see if they work.
try some values to see if they work. That's a good thing, right? To try some values. So like 0 and 1. Let's try those values. 0 and 1 are equivalent, right? Right? So let's try, that would be some scratch work. Let's try 0 and 1. Okay, 0 and 1 have the same class because they differ by an integer. So what's cosine 2 pi of 0? It's 1, right? Right, yeah. And then cosine 2 pi of 1 is also 1. So let me just remind you about how the unit circle. So recall. Right, so we have this unit circle. Right, and so given a theta here, this is cosine of theta, sine of theta. Right, and this is this angle theta. And theta is equal to 0 is up here. Theta is equal to 2 pi is like down here. So it wraps around. Okay, and so these are the coordinates here. So this has x squared plus y squared is equal to 1. Okay, so this is really the x value, and this is really the y value. So cosine squared plus sine squared is really equal to 1. Right? So that's what this unit circle is saying. So when theta is equal to 0, right, the x value here is 1. Right? So this is the point 1, 0. Right? And when theta is equal to pi over 2, that's this number here. So that's a quarter of that. Right? This is the point 0, 1. So cosine of pi over 2 is 0. Okay? So that's the x coordinate here. Okay? So this is really measuring the x coordinate around this thing. Okay. So this is what we're talking about, the unit circle. So for example, in this function, cosine of 2 pi and cosine of 0 are the same value here. So cosine of 2 pi is when you go here, and then we wrap around once, and that's cosine of 2 pi. Okay? So it works for the values 0 and 1. Okay? So for the general proof, what should I do? So we need to check that equivalent inputs have equivalent outputs. So we suppose that we have equivalent inputs, right? So suppose that x is equal to y. Okay, so this means that x minus y is an element of z. Or, so here x and y are real numbers. Okay, and we're supposing that they're equivalent real numbers. Or let's do s and t, so to match the notation, so we don't confuse with the x's and y's are there. So st, st. So s minus t is something like this. Or that that there exists some n in z such that s minus t is equal to n. All right? So we need to show that they have equivalent outputs. So we need to show cosine of 2 pi s is equal to cosine of 2 pi t. Okay, so this is equivalent inputs, and this is equivalent outputs. So this is what we need to prove. Okay, so let's just write down cosine of 2 pi s. Okay, so cosine of 2 pi s, so this is equal to cosine of 2 pi. Okay, and this is equal to t plus n, where n is an integer. Cool? Okay, so this is equal to cosine of 2 pi t plus 2 pi n. Okay, does anyone have a suggestion? Yeah.
I was gonna say for the bottom side of the first board, where it would either be two cases of like s minus t equals 1 already, or s minus t over n equals 1, right? Or no? Am I thinking about that wrong?
I guess you could do s minus t over n is equal to 1. Those are two cases. I mean, that's two cases. You could break it up into those cases if you wanted to. That's a valid thing to do. But that would, so one reason maybe why not do that is because that would involve an extra division. It's a reasonable thing to try.
I was thinking because like the difference between them is either already 1 and you have what you want, or the difference between them some integer that would, once you divide by n, equals 1.
Yeah.
If that makes sense. So like it'd either be like 0 to 1, or like if you had like 0 to 2 and then divide that by 2.
Uh-huh.
It's like shrink it back into the range you want.
That's definitely true, right? It's true. And you can try proceeding like that. That's just not the way I decided to proceed. Okay? But that would make the thing that I'm going to do right now a little bit more complicated, right? So, what you can do, so what I'm going to do now here is I have a sum of angles, right? Do you guys remember this? So I'm going to use the sum of angles formula, right? So this is cosine of 2 pi t cosine of 2 pi n minus sine of 2 pi t sine of 2 pi n. Okay, so what's that equal to? So what's cosine of 2 pi n? 2 pi t, this is 1, right? Because we're just going like that. We're going around, or we're going this way. Okay, so it's negative. Okay? And then this one is 0. Times 0, right? And so this is just cosine of 2 pi t, right? So we're there. You know, we showed that equivalent inputs have equivalent outputs. So since we showed we are done. Okay? So this is this well-definedness for equivalence relations. Any questions on that? Okay, what did I do here? So this is the double angle formula, or sum of angles. From trig. Okay, so that's the sum of angles formula. All right. So let me see where we are. Okay. And we're 2 minutes, right? Yeah. Okay. So let me just say. Okay, that's all the thing I have about well-definedness of functions. Let me just state real quick the official definition of the real numbers, so you guys can see. This is the thing I said. It's kind of like out of context in this. It didn't really fit so cleanly, but I'm just going to tell you the official definition of the real numbers and how it involves an equivalence relation, just so you guys have seen it once. Okay? So there's two official definitions. One's due to Cantor, one's due to Dedekind of R. Okay? So this involves an equivalence relation. Okay? So this is Cantor's version. So R is the equivalence class, so classes of convergent, so let's say convergent sequences of rationals modulo an equivalence relation. Okay? So the definition of convergent So the definition of the convergent says the following. It says that, so an, a sequence, this thing is convergent if and only if, for all epsilon, there exists some natural number, or large natural number, such that for all n and m natural numbers, if n and m are large enough, this implies that the difference between these guys is less than epsilon. Okay, so that's the definition of convergent. And then we define an equivalence relation between two guys. So we have that an and bn. So this is the equivalence. So this is true if and only if. So for all epsilon in the rationals greater than 0, there exists a natural number here such that for all n and m in the natural numbers, if n and m are greater than or equal to n, this implies that an minus bm are less than epsilon. Okay, so so one of the things you'll have to do in 241, right, is you'll check that that's an equivalence relation. Okay, so you take sequences. You have sequences that satisfy this proposition, sequences of rational numbers. Once you have sequences of rational numbers that satisfy this proposition, you check that this is an equivalence relation, and then you take the classes of sequences, right, equivalence classes of sequences under this equivalence relation, and that's how you officially define the real numbers. Okay, so that's like how the real numbers are defined. Okay, so now you've seen another use of equivalence classes.